Hello there, and welcome to Sleepy Science Stories. It's good to have you here again, wherever here happens to be for you tonight. Maybe you're lying still beneath a soft blanket. Maybe the lights are low, the air a little cool. Perhaps the hum of the room has faded into something gentle and distant. Let your breath find its rhythm, slow, quiet, and easy. Outside, the world turns through shadow. The stars above move too, though their motion is far slower written across millennia. Each one hums with its own light, a language of gravity and time. And somewhere out there, in the deep black between those stars, lie places where that language changes completely. Places so strange that time itself bends, so heavy that even light cannot leave. Tonight we drift toward one of those regions, into the mystery of black holes. Not to fall into them, but to rest beside their quiet gravity, to understand what they are and why they might hold the secret to space and time themselves. If these calm journeys through the cosmos help you slow down and rest, a gentle like or soft tap on subscribe helps this little corner of the universe find other sleepy minds who might need a moment of quiet wonder too. As we begin, soften your gaze even if your eyes are closed. Let your thoughts become light like dust moving through air, and let your mind drift among the stars. A black hole is not truly a hole. It is not an object, nor a gap, nor a tunnel to somewhere else. It is a region, a place where gravity becomes so powerful that it traps even light, bending the rules of time and space until those rules almost vanish. The name itself, black hole, suggests emptiness, but that is not quite right. A black hole is full, impossibly full. It holds mass so dense, so compact, that the normal structure of space collapses around it. Matter no longer behaves as matter. Time no longer behaves as time. What remains is a geometry of inevitability, a quiet whirlpool carved into the fabric of existence. To understand one, you have to imagine gravity not as a force pulling objects downward, but as a shape. Einstein showed us that space and time together form a fabric soft, continuous, responsive. Every object with mass presses into that fabric, curving it slightly. The Earth makes a shallow indentation, the Sun a deeper one. But a black hole curves space so severely that the indentation becomes a pit without end. The curve turns inward and keeps turning until there is no way out. Even light, the swiftest traveler, cannot find a path that escapes. That is why it appears black, not because it lacks substance, but because it traps all evidence of its presence. If you were to travel toward one, the first thing you would notice is how quiet the universe becomes. Light around you bends in strange arcs. The stars ahead of you stretch into crescents. The region ahead seems darker than the rest of the sky, not as if shadowed, but as if the idea of brightness has been erased. At a certain distance, there is an invisible boundary, a one-way surface known as the event horizon. This horizon is not a solid wall, not a barrier in the usual sense. It is a threshold defined by motion. Inside it, every path that could be taken, every trajectory, every beam of light curves inward. Outside it, escape is still possible. Cross that boundary and motion itself changes direction. All arrows of time point in. If you were hovering far away watching an object approach this boundary, you would see something strange. The object, a star, a planet, a spacecraft would seem to slow as it approached, moving ever more sluggishly, as if caught in a syrup of time. Its light would stretch into redder and redder tones, fading into darkness until it disappeared completely. From your perspective, it would never quite cross the horizon. It would simply fade frozen in an endless moment. But if you were the traveler falling in yourself, the story would unfold differently. As long as the black hole was large enough, perhaps millions of times the mass of the sun, you might not feel anything unusual when you crossed the horizon. No jolt, no flash, no sensation that you had passed a limit. Space would appear smooth. The crossing would be silent, featureless. Only much later, deeper within, would the forces begin to rise. But by then, you would already be beyond communication, beyond return. This is one of the most profound dualities in physics. From outside, time seems to stop at the horizon. From inside, time continues as usual. Both are true, depending on where you stand. The universe allows each observer their own reality. At the heart of the black hole lies something even stranger, the singularity. It is often pictured as a point infinitely small and infinitely dense. But words like small and dense lose their meaning there. At the singularity, the known laws of physics collapse. Our equations produce infinity's quantities that cannot exist in nature yet emerge when we try to describe it. The singularity is not really a place in space. It is a moment in time where the future ends. To fall into a black hole is to move toward the end of your timeline, not the center of a location. In a sense, it is not so much a destination as it is a final event, the boundary of knowable existence. And yet, this extreme frontier is not destruction alone. It is creation, too. Black holes form when massive stars reach the end of their lives. After burning through their fuel, they can no longer hold up against the inward pull of gravity. The core collapses, shrinking smaller and smaller until it vanishes from ordinary sight. The outer layers explode outward in a supernova, scattering elements across the galaxy, carbon, oxygen, iron, the building blocks of planets and of life. What remains behind is the remnant, a seed of immense gravity, a black hole. There are different kinds. Some are only a few times heavier than the sun. Others are millions or billions of solar masses, the supermassive black holes found at the centers of galaxies. And there may be smaller ones, still primordial black holes formed in the earliest seconds of the universe when matter was packed so densely that small regions could collapse under their own weight. If they exist, they would be microscopic, yet more massive than mountains. They would whisper through space unseen tiny pockets of curvature left over from creation. Despite their variety, all black holes share the same simplicity. Once a black hole forms, it forgets almost everything about what created it. Its entire identity can be described by only three numbers: mass, spin, and charge. Nothing else. Not the shape of the star that collapsed, not the elements that composed it, not the history of its atoms survives as separate information. This is sometimes called the no-hair theorem. Black holes have no distinguishing features beyond those three. They are the ultimate minimalists of the cosmos. But minimal does not mean simple. Around them, space itself is dynamic. Matter that falls inward does not vanish instantly. It swirls into a disk compressed and heated by friction until it glows brighter than a million suns. This ring of light, the accretion disk, is what telescopes see when they capture images of black holes. The black interior, the dark circle at the center of those famous pictures, is not the hole itself, but its shadow, the silhouette of the event horizon against the luminous ring of falling gas. If you could stand near one far enough to be safe, yet close enough to see, the view would defy logic. Light from stars behind the black hole would bend around it, forming a perfect ring of reflected images. You would see the sky wrapped around itself, curved by gravity. In every direction, the universe would appear distorted, a funhouse mirror made of space-time. The stars would stretch and swirl their light, taking many paths to reach your eyes. You might even see multiple images of the same star, one delayed by minutes, another by years, all converging at once. Black holes are not empty. They are full of space that has been stretched and twisted, compressed into new shapes of meaning. In their gravity, the clock of the universe runs differently. Time itself slows curves and folds. To look into a black hole is to look into the mechanism of time. To study one is to glimpse the architecture of reality. The paradox deepens when you realize how many of them there are. For decades, astronomers thought of black holes as rare cosmic accidents scattered here and there. But the truth is far larger. Nearly every galaxy we have observed contains a supermassive black hole at its core. Our own Milky Way holds one Sagittarius A about 4 million times the mass of the Sun. It sits quietly at the center, surrounded by swirling stars, whose orbits reveal its hidden pull. Even though it's invisible, its gravity defines the rhythm of the galaxy. We orbit its influence without ever touching its edge. These central black holes seem to act as engines of galactic evolution. They feed on nearby matter, sometimes erupting in vast jets of energy that stretch across intergalactic space. The material that doesn't fall in is blasted outward, shaping the formation of new stars, redistributing elements and influencing how entire galaxies grow. They regulate creation through destruction. They are, in a sense, cosmic gardeners, pruning and guiding the universe's structure. When black holes merge, when two massive centers collide, they release gravitational waves, ripples in space-time itself. These waves travel across the cosmos, stretching and compressing the fabric of existence as they go. When they pass through Earth, we can detect them, faint shivers, measured by instruments like LIGO and Virgo. Each detection is a whisper from the deep past, a record of two invisible titans uniting. Through those signals, we have learned that black holes are not isolated curiosities. They are everywhere, common as stars once were in our myths. The night is filled with silent gravity. And yet, for all their power, they remain profoundly simple. Each one is like a clock, with only one hand ticking slower and slower as it grows larger. Each is a boundary, not only in space, but in knowledge, a reminder that the universe still holds secrets that resist our language. If you think of a black hole as a mouth devouring all that enters you, miss half its beauty. It is also a mirror. When we look at it, we see reflected our own need to understand. Our curiosity bends toward it as surely as matter does. It reminds us that every discovery carries an event horizon, a limit to what we can know from the outside. And yet, we keep drifting closer, drawn by the gravity of not knowing. Black holes also blur our most basic categories. They are neither matter nor energy, neither object nor place. They are behavior, space-time behaving in a particular way. They show us that the universe is not made of things, but of relationships, curves, patterns of interaction. And, in their silence, they teach us something about time, that it can be elastic, malleable, different for each observer, yet still consistent. They remind us that what feels like an instant for one being may feel like an eternity for another, depending on where they stand in the web of gravity. Imagine drifting near the edge of one just outside the horizon. The light of distant galaxies arcs around you. The blackness in the center is total, deeper than shadow. Every sound, every motion, every thought slows. You are still within the universe, but it feels as though you have stepped into a different version of it, one where the usual sense of before and after begins to dissolve. You are not falling, not rising. You are simply existing in curved time. From here, it's easy to see why black holes fascinate both scientists and dreamers. They sit at the intersection of extremes between existence and absence, between order and mystery. They are the universe's way of asking its own questions. What happens to space when time stops moving? What happens to information when it crosses a line that cannot be crossed back? Where does meaning go when the medium itself folds away? Perhaps that is why we are drawn to them at night, when our own world is quiet, when we can sense the weight of time pressing softly against our awareness. In the hush of darkness, we feel something of their stillness within us, that gentle, infinite patience with which they wait, invisible but present at the heart of everything. Black holes are not the universe's monsters. They are its meditations. They remind us that even in silence there is motion. Even in darkness there is structure. Even at the edge of understanding, there is peace. And the deeper you gaze into that peace, the more it gazes back, a vast, unblinking eye made of gravity and time, watching gently as the stars drift by. Even as we sleep, the galaxy turns. Black holes hum softly at its center, steady and eternal, marking the rhythm of creation. Their gravity shapes our world, though we never feel it directly. Their mystery shapes our curiosity, though we cannot touch them. Quietly, slowly, endlessly, the night continues. You can still feel the quiet weight of the last thought, the image of a horizon where time slows the sense of falling, not through space, but through understanding itself. The universe drifts onward as we rest beside that horizon. Stars hum faintly in the background. Their light travels across millions of years, bending around invisible wells of gravity. And in that slow movement, we find a deeper question. What makes the black hole so different, so sacred to physics, so impossible to ignore? It is because it asks us to choose between two truths that should never disagree, yet do. In all of nature, there are two great rulebooks, two languages through which reality speaks. Each is complete within its own realm, each perfect in its precision, and yet they do not fully understand each other. The first is general relativity, Einstein's grand geometry of space-time. It tells us that mass and energy are not separate from space and time, they shape them. They bend the universe, and in return that curvature tells matter how to move. In relativity, gravity is not a pull. It is the shape of the path things must follow. Relativity describes the vast and the heavy planets and stars, galaxies, and cosmic expansion. It paints space as a smooth continuum, a fabric that curves gently under the presence of matter. It is graceful, infinite, unbroken. The second is quantum mechanics, the rulebook of the very small. It lives not in the stars, but in atoms. Not in galaxies, but in electrons. Where relativity speaks of smooth curves, quantum mechanics speaks of sudden jumps, tiny probabilities, and the shimmer of uncertainty that lives in every particle. Here, matter does not exist as solid points. It exists as waves of possibility spread through space until we look, and only then, only in that act of observing, does it choose one form, a position, a spin, a moment in time. Quantum mechanics is sharp, where relativity is smooth. It vibrates, where relativity drifts. It deals not with the continuous, but with the discrete bits of energy quanta, of light packets of being. Both are correct, and both describe a different face of the same universe. But a black hole sits at the intersection of those faces. It is where both rulebooks must be opened at once, and they do not agree on the ending. Imagine this. At the edge of a black hole, space stretches so much that time slows nearly to stillness. Gravity is at its most extreme, and Einstein's equations describe it beautifully. They tell us how stars spiral inward, how orbits decay, how the event horizon forms. But inside, on scales smaller than an atom, where space curves infinitely, the quantum world should take over. And in that transition, relativity begins to break. Its fabric tears where gravity becomes infinite, where curvature no longer has meaning. To truly understand what happens there, we would need a quantum theory of gravity, a single framework where space-time itself is quantized, built from indivisible bits woven from the same threads that underlie matter and light. This theory would merge the continuous with the discrete, the curved with the uncertain, the vast with the minute. We don't have it yet. We have pieces, glimpses, but the full picture still hides beyond the event horizon of knowledge. And that is why black holes are sacred. They are not only cosmic objects, they are crossroads. Every time one forms, the universe creates a place where both sets of laws must meet. A place where the smooth curves of space-time collide with the jittering foam of quantum fields, where order becomes probability and certainty dissolves into structure we can almost but not quite describe. To feel how delicate this boundary is, imagine shrinking yourself smaller and smaller until your entire body is smaller than a grain of dust, smaller than an atom, smaller even than a proton, until you are a quantum traveler, a ripple of energy drifting through the fields of the universe. Now imagine falling toward a black hole. From your perspective, you move through smooth curvature as relativity describes. But your own existence, the way you behave, the way you vibrate, is ruled by quantum laws. You are both wave and particle, both energy and matter. You cannot stop behaving that way just because gravity becomes strong. So as you approach the horizon, you drag your quantum nature with you, and in doing so, you reveal the tension between the two great rulebooks. Relativity says the horizon is silent smooth, nothing special. Quantum theory whispers, nothing is ever truly empty. Vacuum itself is alive with motion. Between those two truths lies a paradox so powerful that it redefines what we mean by understanding. In quantum mechanics, even empty space is not truly empty. It is a restless field, a sea of energy that flickers in and out of existence. Particles and antiparticles appear and vanish constantly, borrowing existence for a moment before disappearing again. This dance happens everywhere in your room, in the space between stars, and even along the edge of a black hole. At that edge, however, something subtle occurs. The gravitational field is so intense that the pair, the particle and its mirror, the one with opposite charge or spin, can be pulled apart. One falls inward, the other escapes. And from that escape a faint glow emerges. Hawking radiation. The idea proposed by Stephen Hawking in the 1970s was one of the most astonishing revelations of modern physics. It told us that black holes, once thought to be eternal prisons, might not be eternal after all. They could leak. They could evaporate. They could radiate heat slowly, gently, over incomprehensible timescales. For a large black hole, the process is painfully slow, billions upon billions of years. The radiation is faint, nearly undetectable, but in principle, the black hole loses mass as it glows. Eventually it would fade, shrinking to nothing. This discovery did something more profound than change our view of black holes. It forced us to confront an impossible question. What happens to all the information that falls in? In quantum physics, information is sacred. It cannot be destroyed. The position, spin, energy, and relationships of particles, no matter how they change, must be preserved. Even if a system evolves into something new, the total information of what it once was is still embedded in its state. But black holes seem to erase that rule. If matter falls in and never escapes, its information appears lost forever. If the black hole evaporates into simple radiation, featureless random, then the information it once contained has vanished completely. That breaks the most fundamental law of quantum theory. This is called the black hole information paradox. It is a riddle so deep that physics itself bends around it, much as light bends around a singularity. For decades, physicists have tried to resolve it. Some proposed that the information really is lost, that black holes mark the end of determinism, that the universe can erase history. But that would mean the rule books themselves are inconsistent, that the quantum world and the gravitational world cannot both be true. Others suggested that information is not destroyed. It is somehow encoded in the radiation that leaks out. That each faint photon escaping the black hole's edge carries with it an infinitesimal trace of what once fell in. That the glow is not random after all, but subtle, ordered, and rich in hidden structure. In that view, the black hole acts like a storyteller. It keeps its secrets for eons, then whispers them back to the universe in the faintest possible light. To follow that idea further, we have to change how we think about space itself. When we look at a black hole, it is tempting to imagine it as a three-dimensional void, a sphere containing an unknown interior. But the mathematics suggests something else, something deeply counterintuitive. The entire content of the black hole might be stored not within its volume, but upon its surface. The amount of information a black hole can contain is proportional not to how big it is inside, but to the area of its event horizon. Each square of surface, each tiny patch, seems to correspond to a bit of information, as if the universe writes data on its edges. This is known as the holographic principle. It suggests that a black hole, and perhaps all of reality, is like a hologram, a three-dimensional experience encoded on a two-dimensional surface. Inside and outside are not separate. They are reflections of the same information written in different languages of geometry. To think of the universe this way is to soften the edges of space and time themselves. It means that what we call reality might emerge from patterns of information woven together in ways we can only begin to imagine. Gravity in this picture is not fundamental. It is an effect, a large-scale echo of countless microscopic correlations between quantum bits of data. Some physicists even suspect that space-time itself is an emergent phenomenon, a structure born from the entanglement of quantum states. In that sense, black holes are not the end of understanding, they are the bridge to the next layer of it. They are laboratories of information where the universe experiments with how meaning is stored, shared, and preserved. If you look back at the two rule books, Relativity and Quantum Mechanics, you can see now how the black hole ties them together. Relativity provides the stage, the curvature, the event horizon. Quantum theory provides the shimmer, the energy, the uncertainty. The two cannot be separated. At the horizon, they overlap their pages, fused like layers of light and shadow. Perhaps that is why black holes appear so calm. They are the equilibrium point between opposites, where chaos and order coexist, where the universe balances its equations perfectly and hides the answer behind silence. If we could stand outside one for eternity watching it glow, we would see time unfold like an immense spiral. The whole would shrink imperceptibly, its mass decreasing atom by atom, its glow growing slightly hotter as it ages. And in that light, faint beyond imagining, all the history of what it once consumed would be returning encoded in soft quantum whispers. To the universe, the black hole is not a devourer. It is a librarian. It keeps every record, every event, every atom's story, and returns them slowly to the cosmic archive. We may never see this process directly. The time scales are too long, the radiation too faint. But the principle itself reshapes how we think about existence. Nothing, it says, is truly lost, not in black holes, not in time. And so when you picture that dark horizon again, that silent edge where even light cannot leave, know that it is not empty. It is filled with the memory of everything it has touched. It holds the dance of matter and energy, the fusion of gravity and quantum fire. It holds the meeting point of all our understanding. The black hole is a teacher written in darkness. It reminds us that every mystery is also an invitation, that boundaries in science are like horizons. They look like endings, but they are beginnings in disguise. Quietly, slowly, endlessly. The universe continues to breathe its two great rule books fluttering in the cosmic wind. And somewhere in the pages between them, gravity and quantum light are learning to speak the same language. You might still feel the weight of the last thought, how two great languages, gravity and quantum, meet at the horizon, their words melting together in a field of soft contradictions. That is where we begin again, in the trembling quiet between certainty and wonder. The black hole, once thought to be eternal silence, turns out to speak not in bursts of light, but in the faintest possible whisper of heat. And that whisper, discovered through thought and not through sight, became one of the greatest ideas of the 20th century. It began as a paradox in the mind of Stephen Hawking. He was thinking about vacuum, that perfect stillness we imagine as empty space. But physics, especially quantum physics, tells us there is no true emptiness. Even the void hums faintly with energy. It flickers like the surface of a pond disturbed by invisible wind. In that flickering, pairs of particles appear and vanish constantly. They are called virtual particles, not imaginary, but transient, borrowing existence for a breath of time. One is matter, the other antimatter. They cancel each other as quickly as they arise. The universe, in its quantum bookkeeping, balances to zero. But near the edge of a black hole, that balance can be interrupted. Imagine two such particles forming at the very edge of the event horizon. Normally, they would destroy each other instantly. But here, gravity intervenes. One particle falls inward, crossing the boundary that no light escapes. The other escapes outward, freed from its partner. To an observer far away, that escaping particle looks like radiation, as if the black hole itself is glowing faintly. But the glow does not come from inside the black hole. It comes from the edge, from the restless energy of space itself. And because energy is conserved, the escaping particle must take something from the black hole, in return a little bit of its mass, a small piece of its stored gravity. Over time, as these exchanges continue, the black hole loses weight. It shrinks. It grows hotter, its faint glow intensifying as it ages. Eventually, in times far beyond human comprehension, it could evaporate, completely disappearing into a final flash of pure radiation. That quiet evaporation is called Hawking radiation, and it changed everything we thought we knew about black holes. Before Hawking, black holes were thought to be perfect, one-way systems, things that could only consume, never release. They were the ultimate prisons of physics. But Hawking's equations said something gentler. Nothing is completely silent, not even the void, not even the blackest hole. There is always a murmur, a low, patient exhale of energy. And through that breath, black holes reveal a truth about the universe itself, that even in absolute darkness, the rules of quantum nature still apply. Even the most powerful gravity cannot silence the quantum hum. The discovery united ideas that had never met. Here was quantum mechanics playing its tiny probabilistic tune on the curved strings of Einstein's spacetime. Hawking had created a bridge, not a complete one, but a glimpse of what such a bridge might look like. The smallest and largest scales of existence were speaking through the same equation. But with that bridge came another question, one that grew into a crisis of meaning. If black holes radiate, if they can evaporate entirely, then what happens to everything they have swallowed? Where does the information go? Information is not just about words or data. In physics, information means the complete description of everything in a system. The positions of particles, their velocities, their spins, their quantum connections to one another. It is the universe's memory of itself. And according to the laws of quantum mechanics, that memory cannot be erased. It can change form, scatter, diffuse, but it cannot disappear. The total information of the universe remains constant, like a sacred balance between past and future. But if a black hole evaporates into simple heat, featureless and random, it seems to destroy that balance. all the patterns of what once fell in the shape of a star, the data of a planet, the molecules of an explorer's body would be gone, forever lost, replaced only by radiation without history. That cannot be true, and yet it seems to be. This is the black hole information paradox. A tension between the two rule books so deep that it challenges the foundation of physical law. For many years, Hawking himself believed that information truly is lost in black holes. It seemed elegant, a final boundary for knowledge, a place where the universe forgets. But others could not accept that. They argued that nature does not erase, it only hides. The universe, they said, is far too careful to allow its own history to vanish. So began a decades-long debate. Entire generations of physicists devoted their careers to tracing the faint logic of this paradox. If information was preserved, how could it be? Where could it go? Some imagine that the information remains trapped, encoded in subtle fluctuations at the horizon, not destroyed, just scrambled, stored in patterns of gravity itself. Each bit of matter that falls in might leave a faint fingerprint, a distortion in the quantum state of the horizon. Later, as Hawking radiation leaks out, that fingerprint might imprint itself onto the outgoing light. It would mean that black holes are not featureless after all. They would be vast archives, libraries, that store information in a code too complex to read. Every photon they emit would carry a whisper of what once was. Others proposed something more radical, that information could escape through hidden quantum connections between the inside and the outside of the hole, threads of entanglement that tie together regions of space-time we thought were separate. In this view, the event horizon is not a wall, but a woven membrane of connections. It looks solid, but it is porous to information. Entanglement reaches through it like roots through soil. The universe remains whole. Its knowledge remains continuous. To understand why this is possible, we need to return again to quantum theory itself. When two particles interact, they can become entangled, their properties linked, so that a change in one is instantly reflected in the other, no matter how far apart they travel. Entanglement is not a transfer of signals. It is a shared definition. The universe does not think of them as two things. It thinks of them as one. When a particle falls into a black hole, its entangled partner remains outside. If information were truly destroyed, that partner would lose its meaning, its definition. The universe would break its own logic. So the information must remain somewhere woven into the structure of space, preserved in patterns we cannot yet decode. This idea inspired one of the most elegant metaphors in modern science, the holographic universe. If information about what falls in is stored not inside the black hole, but on its surface, then perhaps the entire universe works that way. Perhaps everything we see in 3 dimensions, every star, every planet, every thought is the projection of information encoded on a vast, distant boundary. Like a hologram on a film, the whole of reality could be a higher dimensional image emerging from a lower dimensional code. The inside and the surface are the same truth told from different perspectives. If that is true, then black holes are not just laboratories of gravity, they are mirrors of existence itself. They show us that the boundary between in and out, between object and information, is not fixed. It is fluid. Reality may be a kind of computation, a cosmic algorithm unfolding over eons, its logic etched into the skin of space. Modern physics calls this idea the holographic principle, and it reaches far beyond black holes. It suggests that space and time themselves might arise from information that the geometry of the universe is a map of relationships between bits of data. The distance between 2 points is not a physical gap, but a measure of how much information they share or lack in common. In that light, gravity becomes the result of information trying to organize itself. The universe is not a stage, but a network of connections adjusting constantly to maintain balance. Black holes in this view are not exceptions to the rules. They are the purest form of them regions where information density reaches its limit. The event horizon is the surface where storage capacity maxes out a boundary written in units of Planck area, tiny squares only 10 to 66 centimeters across. Each square could hold a single bit, the smallest yes or no, the smallest possible piece of meaning. If you could somehow stand outside a black hole and see the quantum code written on its surface, it might look like a tapestry of flickering lights, bits turning on and off patterns rearranging as new matter falls in. To you, it would appear motionless, but on cosmic timescales, it would shimmer softly like a slow heartbeat of reality. And when the black hole radiates, each photon that escapes would carry away one of those bits, a syllable of the story being released back into the universe. Over trillions upon trillions of years, that story would complete itself. The black hole would vanish, but the tale it had contained would remain written in the particles it left behind, scattered across the cosmos, still coherent, still whole. The universe forgets nothing. It only changes the form of its remembering. But the paradox remains powerful because it touches something deeper than equations. It touches our intuition about loss and permanence. It asks whether there can ever be true disappearance. And in a way, it echoes the human fear of forgetting the anxiety that what we love, what we build, what we experience might someday be erased without trace. The black hole says otherwise. It says that even when form dissolves, the pattern remains. Even when the structure collapses, the meaning endures hidden in the quiet glow of entropy. This is not just physics. It is philosophy written in mathematics. It tells us that everything that happens, every spark of energy, every ripple of consciousness, is etched into the deep memory of the universe. The past cannot be undone. It can only be transformed. If you listen closely to this idea, you might hear its rhythm matching your breath. Inhaling, exhaling, creation-evaporation, information drawn inward then released again. The black hole is not the end of time. It is time's reflection. The same way sleep is not an absence of awareness, but a place where awareness reorganizes itself. The black hole is not destruction, it is translation. Matter becomes energy, structure becomes pattern, form becomes story. And in that story, the two great rule books we spoke of before write their shared sentence at last. Nothing is lost. Everything changes shape. The paradox may never fully close. Perhaps that is its purpose, to keep us curious, to keep science humble, to remind us that knowing is an infinite horizon. Black holes glow faintly in our imagination now, not just as darkness, but as teachers of light. Their radiation is so slow, so soft, that no human will ever witness a single one evaporate. Yet the truth of their whisper reaches us already, carried on the mathematics of thought, on the language of patient curiosity. Even in nothingness, there is motion. Even in silence, there is heat. Even in disappearance, there is record. Quietly, slowly, endlessly. The black hole breathes out its secrets one photon at a time. And somewhere in that faint radiance, the universe keeps its promise to remember. The faint whisper of Hawking radiation still lingers in the mind, that slow evaporation, that patient exhalation of light. The black hole, once thought silent, becomes a storyteller, returning the memory of what it has swallowed bit by bit, photon by photon, until nothing remains except the echo of understanding. From that thought, something begins to shimmer, an even stranger possibility born from the paradox we just touched. That information might not be trapped inside the black hole at all, but gently written on its surface. That the interior could be an illusion, a projection of information stored at the boundary. And if that is true for black holes, then perhaps it is true for everything. Perhaps the entire universe behaves this way, a vast unfolding hologram, where depth is not distance, but an emergent property of data woven into the surface of space itself. When you hear the word hologram, you might imagine a sheet of film holding the pattern of a three-dimensional image, flat, delicate, glowing only when light passes through it. Each fragment of that film contains the whole picture, encoded not in color, but in interference patterns of light waves combined and frozen into form. In the same way, the universe may hold its image within interference patterns of quantum information. Every region of space could contain echoes of every other woven together by entanglement, that mysterious connection between particles that defies distance and time. The cosmos could be a single coherent holographic film, and we are beings living within the projection three-dimensional shadows cast by an underlying web of pure data. This idea does not lessen reality. It deepens it. It tells us that what we call space may not be empty at all. It may be a texture of relationships, a dense field of information where each bit knows its neighbors. We move through it. We breathe within it, our own atoms whispering to the field as we go. The connection between holography and black holes was first seen not in light, but in mathematics. Physicists discovered that the entropy, the measure of disorder, or the information content of a black hole, is proportional not to its volume, but to the area of its event horizon. This is profoundly strange. Most objects store information in proportion to how much space they occupy. A hard drive, a memory chip, a brain, each holds more data when it has more interior room. But black holes defy this rule. All their information lives on the surface, as if the inside does not truly exist in the way we imagine. That finding was the seed of the holographic principle, a principle that soon grew far beyond the physics of black holes. It suggested that reality itself, every region of spacetime, might be describable by data encoded on a lower dimensional boundary. In short, that our three-dimensional world could be the holographic projection of information written on a vast cosmic surface. The first glimmer of this came from the work of Gerard 't Hooft and Leonard Susskind, who saw that black hole thermodynamics, the relation between surface area temperature and entropy, hinted at a general rule. Later, a more specific realization came through the ADS-CFT correspondence, a discovery in string theory that gave the holographic principle mathematical form. It showed that a universe with gravity like ours could be equivalent to a different kind of theory without gravity living on the boundary of that space. The two descriptions are mirrors of each other, the interior geometry and the surface code. One is curved space-time, the other is a network of quantum fields. And yet they describe the same physical reality. It's as if the universe is bilingual, fluent both in geometry and in information, each language a reflection of the other's grammar. When a black hole forms, the surface becomes the bookkeeper of everything that falls in. The bits of data do not vanish. They are rearranged and coded along the horizon in an exquisite invisible pattern. Space and time themselves arise from that encoding. Each line of information helps define the curvature, the distances, the flow of time we perceive. This means that reality, as solid as it feels, might be built from relationships rather than things. From information, not substance. To see how deep this idea goes, imagine zooming in on a region of space-time. What you might find is not smooth fabric, but a lattice of connections, like a cosmic web of information nodes, each linked to many others through entanglement. The strength of those connections determines the shape of space, the rate at which time flows, the way gravity pulls. Space in this sense is not a stage where matter acts. It is the play itself woven from interactions between qubits of information. And here, quietly, quantum computing enters the story. In a quantum computer, information is stored not in binary bits, zeros or ones, but in qubits, quantum bits that can exist in many states at once, a superposition of possibilities. Two qubits can be entangled, meaning their states are linked no matter the distance between them. A change in one ripples through the other instantly, not as a signal, but as a shared definition of existence. This is not unlike what happens in the holographic universe. Each point of space, each grain of space-time may hold entangled information about its neighbors, just as qubits in a quantum computer share knowledge beyond physical contact. The cosmos may operate through similar principles, a vast quantum network computing itself into being. Some physicists even propose that the equations of space-time geometry mirror those that govern quantum error correction. Error correction is how quantum computers preserve information. Because qubits are fragile, susceptible to noise and loss, they must store data in overlapping patterns so that no single disturbance can erase meaning. Information is protected by redundancy. Black holes seem to do something similar. Their surface encodes data redundantly, so that even as they radiate and evolve, the underlying information is preserved. It's as if the horizon itself performs a cosmic version of quantum error correction, ensuring that the universe's memory never truly fades. This connection between black holes and quantum computation is not just a metaphor. Mathematically, it runs deep. The way information is stored and scrambled at a black hole's horizon follows the same principles that define a robust quantum memory. Every photon of Hawking radiation that escapes carries a trace of the entangled structure that remains, and together they preserve a complete, though unreadable, record of the past. In this way, the black hole behaves like the ultimate quantum computer, compressing, encoding, and safeguarding data with perfect efficiency. It does not compute in time as we know it, but in geometry, its logic is curvature, its storage medium space-time itself. It processes information not by flipping bits, but by shaping the flow of time. You can almost imagine it. An invisible mind made of gravity, silent, immense, working, not in seconds, but in ages, solving equations through its very being. Each collision of particles near the horizon is a computation. Each ripple in the curvature is a line of code. Each burst of radiation is a line of output, the universe interpreting its own equations in real time. And if this is true for black holes, perhaps the same is true at a gentler scale for all of space. Perhaps the cosmos itself is an ongoing quantum computation. Every atom, a bit; every field, a program; every law of physics, a rule of logic encoded in the deep structure of information. The stars would then be vast processors burning not only with light but with meaning. The galaxies would be networks linking those processors together, and the black holes at their centers would be the ultimate memory nodes, cosmic servers storing the collective data of their galaxies until the end of time. Yet this does not make the universe mechanical. It does not turn wonder into machinery. If anything, it makes the machinery divine a pattern so vast and self-aware that the distinction between process and presence dissolves. We live inside the computation, but also within its beauty. We are both data and witness. Our thoughts, our feelings, our questions are part of the same unfolding algorithm. When we look at the stars, we are the universe reflecting on itself, quantum information momentarily aware of being information. If the holographic principle is right, then what we call inside and outside are illusions of perspective. The world we perceive as three-dimensional may arise from a hidden layer of two-dimensional information. But that does not make it less real. It only means that reality has levels, each one capable of generating the next. Depth itself becomes a form of meaning born from the way information is arranged. It also means that boundaries, like the edge of a black hole, are not walls, but mirrors. They reflect the universe's information back upon itself, preserving balance, maintaining coherence like the surface of a calm sea, holding the sky. Everywhere in nature, we see versions of this same symmetry. The inside reflecting the outside form, mirroring energy information encoded in matter, meaning emerging from silence. If you listen to this concept quietly, it begins to sound almost spiritual. But it remains grounded in mathematics, equations describing how entangled systems produce geometry, how entropy maps to surface area, how time might arise from the flow of information itself. There is poetry hidden in those equations. They say that what binds the universe together is not force, not substance, but relationship. The fabric of existence is woven from the grammar of connection. Every particle knows something about every other. Every bit of light carries a trace of the cosmos that birthed it. Even as we sit here half awake, half dreaming, we are part of that same correspondence, a network of awareness woven through space and time. The holographic principle and quantum computing are not just parallel ideas. They are reflections of the same deeper truth that meaning and matter are inseparable. To understand the universe is to understand how information flows, how it remains whole despite change, how it organizes itself into what we call reality. The next time you look at the night sky, you might imagine the stars not as distant objects, but as pixels in an immense glowing image, a holographic projection of the universe's own information. Each photon that reaches your eyes is part of that picture, carrying within it the entire history of its journey. You are not merely observing light, you are decoding a fragment of the cosmic message. And in turn, your own awareness becomes part of that message, rippling back into the field, altering it, infinitesimally, adding new structure, new entanglement, new possibility. Black holes remind us of this hidden unity. They take what is physical and translate it into information, what is temporal and convert it into geometry. They demonstrate that the boundary between physics and computation, between matter and meaning, between being and knowing, is an illusion of scale. At the deepest level, these are all one and the same. So the universe is not just a stage for information. It is information performing itself. Each galaxy, each atom, each life is a line of code in an infinite unfolding program, not mechanical, but luminous, not digital, but alive. And like all great programs, it contains error, correction, memory, and recursion, the ability to refer back to itself. Perhaps that is what consciousness is, the recursion of the universe looking inward, a feedback loop of awareness formed from starlight and thought. If this sounds abstract, remember the feeling of the first black hole image, that ring of orange light captured by telescopes across the Earth. It was not just a picture. It was the first direct proof that what we theorize about information and gravity is woven into reality. We saw the hologram made visible. We saw space itself glowing with memory. That faint, fiery ring was more than gas and light. It was the handwriting of the cosmos, the universe writing in the language of curvature and heat. Each photon in that ring carried the record of its dance near the horizon, each one bending and blending, recording the shape of space-time itself. We looked into that darkness and saw not emptiness, but precision. Not chaos, but structure. A hologram breathing softly, turning quietly in the dark. If you could close your eyes now and imagine the entire universe as one great hologram, you might picture an endless surface of light, subtle as frost, folded over itself in layers of information. Each point contains the whole. Each flicker holds eternity. And within that surface, within the great computation, you, this moment of awareness, are one of its expressions. A localized pattern of information, briefly aware of being part of the pattern. A self-reflecting bit of light dreaming of stars. Quietly, slowly, endlessly. The hologram breathes. The computation continues. And the universe remembers itself through us. The thought still lingers, the quiet shimmer of the holographic universe. The idea that the world we see may not simply exist, but be encoded like the ripples on the surface of an unseen sea of information. And now, after drifting through equations and imagination, we return gently to the eyes, to the act of seeing. Because even in this cosmos of abstraction, we remain creatures of light. We believe what we can witness, what touches the sensitive layer of our vision. And so we ask, if black holes are invisible, how can we ever see them? To see something that does not emit light, we must look for what it does to light. We must look for the traces of its pull, the bending of the paths that light would otherwise take. We see a black hole not by its presence, but by its absence. A shadow carved into the fabric of brightness. For decades, this was a dream, a thought experiment repeated in dusty observatories and clean white labs. The black hole was a concept more than an image, a word that meant gravity beyond comprehension. And yet, astronomers were patient. they watched the centers of galaxies. They measured the speed of stars whirling around invisible points. They traced the paths of light distorted by unseen masses. Piece by piece, they built a map of what could not be seen. At the heart of our own galaxy, the Milky Way, lies such an unseen center, a quiet region in the constellation Sagittarius called Sagittarius A. It is small as galaxies go just 4 million times the mass of our Sun, and yet it governs everything that orbits nearby: the motions of stars, the dance of gas clouds, the pulse of radio waves that whisper through the interstellar dark. For years, astronomers followed a single star there, S2, as it moved around that invisible point. Its orbit took 16 years to complete a slow ellipse drawn by gravity's steady hand. From that motion, we learned that something unimaginably dense must sit in the middle. No cluster of stars could fit in such a small volume. No ordinary object could hold such mass. The conclusion was inescapable: it had to be a black hole. But knowing is not seeing, and humanity is restless. We longed to look directly into the dark. To photograph something that does not shine, astronomers had to think not like photographers, but like choreographers of distance and time. They built a telescope the size of Earth itself, not in one piece, but in pieces scattered across the planet. From the ice of the South Pole to the deserts of Chile, from mountains in Spain and Hawaii to radio dishes in North America, each telescope listened to the same whisper of light at the same moment, their recordings later stitched together by the patience of computation. This global collaboration was called the Event Horizon Telescope, a network so precise that it could measure the thickness of a single human hair seen from thousands of kilometers away. Its purpose was to capture light that had traveled across intergalactic distances curved by the gravity of a black hole and reached Earth as faint radio waves. The data was immense, petabytes of signals, too vast to send by internet cables. Instead, hard drives were flown by plane, carried by hand, collected like sacred artifacts, to be joined in a single place where the universe's most secret image would slowly emerge. The result in 2019 was an image you may remember: a glowing ring around a dark center, a circle of fire suspended in shadow. This was M87, the supermassive black hole at the heart of a galaxy 55 million light-years away. It is enormous, 6.5 billion times the mass of our Sun. It could swallow our entire solar system and still hunger for more. And yet, when the image finally appeared, it was not terrifying. It was quiet, soft. The light glowed like an ember, like a memory burning slowly through time. The shadow in the middle, that dark absence, was the event horizon's silhouette. For the first time in human history, we had seen the shape of nothingness. The light around it was the last cry of matter spiraling inward, gas heated to unimaginable temperatures turning to light as it fell, painting a ring that marked the boundary between being and beyond. To understand what we were truly seeing, it helps to imagine what light experiences there. Near the event horizon, gravity bends space so strongly that light itself follows curved paths looping around the black hole before escaping. Some photons circle it once, twice, even many times before breaking free. That is why the ring glows more brightly along one edge, because light from that side is bent toward us, amplified by motion and gravity alike. We are not seeing the black hole itself, but the space around it, the place where light forgets which way is forward. It is a boundary between knowable and unknowable, between what returns and what does not. A horizon not just of matter, but of comprehension. Later in 2022, the same collaboration revealed another image, this time, the black hole at the heart of our own galaxy, Sagittarius A. Because it is smaller, its light changes more quickly, making the picture harder to capture. But there it was, the same ring, the same dark center, a cosmic echo scaled differently, but identical in structure. The pattern confirmed what Einstein's equations predicted a century ago. Gravity had once again told the truth. And in that truth, we glimpsed something profound. No matter how far apart they are, no matter their size or mass, black holes all share the same geometry of silence, the same logic of curvature, the same whisper of inevitability. Seeing a black hole is not just about the light we detect. It is also about the light we don't. It is about understanding that visibility is not the same as existence. The universe hides its most elegant truths behind shadows. And sometimes by studying the shape of those shadows, we learn more than light could ever show. In the black hole's image, we are not merely looking into darkness, we are looking into the structure of space-time itself, the bending of reality by gravity's hand. That shadow is geometry made visible. It is space curving around its own absence. But light is not the only messenger. There are vibrations that move through the universe not as light, but as ripples in space-time itself. These are gravitational waves, the soft music of the cosmos. Einstein predicted them a century ago. He said that when massive bodies move, when stars explode, when neutron stars collide, when black holes merge, they disturb the fabric of space-time, sending out waves that travel at the speed of light. For decades, these waves were only a prediction too faint to be detected by human instruments. But in 2015, a signal arrived, a tiny trembling echo in the detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory. It was the sound of two black holes colliding more than 1 billion light-years away. For a brief moment, they danced together in a spiral of impossible energy twisting space-time itself. The collision released more power than all the stars in the observable universe combined, but only for a fraction of a second. The universe rang like a bell and then was still again. That first detection changed everything. It was proof that black holes were not theoretical ghosts. They were real, abundant, alive in motion. Since then, dozens of such signals have been recorded. Black holes merging neutron stars, colliding echoes from the farthest reaches of time. Each one tells a story. Each one confirms that gravity is not silent, that space-time can carry sound without air, that the universe itself is an instrument of vibration. These detections also allow us to measure things that no telescope could ever see. We can weigh black holes, map their spins, estimate their distances. We can listen to the song of creation itself. And in this way, astronomy becomes not only visual, but symphonic. The cosmos reveals itself in many registers, light gravity particles, waves each one a verse in an infinite composition. Together, they form the music of existence, a harmony that spans from quantum whispers to galactic roars. Even as we rest here, eyes closed, breath soft, the universe hums all around us. gravitational waves pass through you now, imperceptible yet real ripples from ancient collisions traveling through your atoms. You are part of the same medium they traverse. You are listening even in stillness. To see black holes, to truly understand them, we must use every sense our species can invent. Light, radio, X-rays, neutrinos, gravitational waves, each opens a different window. Together, they form a composite picture of the unseen. Through them, we learn not only what black holes are, but what seeing really means. Seeing is not about eyes. It is about recognition, about perceiving the patterns hidden in nature's stillness. When we look at that glowing ring around the dark, we are seeing not just matter or motion, but the universe acknowledging itself. A reflection of consciousness written in physics. In the deep time of the cosmos, black holes shape the rhythm of creation. They form when massive stars die, but they also give birth to structure on galactic scales. Their gravity sculpts the arms of galaxies, guiding gas and dust into orbits where new stars can form. They regulate the flow of matter through feedback jets of energy that heat the surrounding space, balancing creation with restraint. Without black holes, galaxies might collapse into chaos. Too many stars too soon. Too much brilliance and no structure to hold it. The black hole's invisible presence brings harmony through gravity. It anchors motion, stabilizes light. Even destruction has its purpose. Infalling matter releases energy, fueling the birth of future stars. Death feeds life. Darkness gives shape to light. As we build new observatories, space telescopes that see in infrared radio arrays that stretch across continents, detectors that listen for fainter and fainter waves, we are not just collecting data. We are expanding the senses of humanity itself. We are learning to feel the universe the way it feels us, through resonance, through connection, through the exchange of energy and information. The James Webb Space Telescope, now unfolding its golden mirror in orbit, looks back in time to the first galaxies, the early structure of the universe, the cosmic dawn when the first black holes were born. Its vision pierces dust and distance alike, seeking the seeds of everything we see today. Perhaps it will find the faint signatures of the first gravitational wells, the first collapses that lit the path toward stars and planets, and eventually toward us. Every new observation is a reminder that we are not separate from these things. The elements that form our bodies, iron, oxygen, carbon, were forged in stars and recycled through the violence of collapse. We carry within us the memory of black holes and supernovae alike. When we look at them, we are seeing our own origins written in cosmic ink. There is a humility in this realization. Our telescopes, our equations, our instruments, all are extensions of the same curiosity that began when early humans looked up and wondered why the sky moved. We are still doing that, but now our questions reach across billions of light years, and still each answer brings more questions. That is how science breathes. That is how wonder survives. If you imagine it quietly now, the black hole's ring glowing faintly against the dark, you can feel its symmetry in your own heartbeat. A slow pulse, a rhythm written in gravity. Light moves, matter falls, time curves, and through it all, a deep, unbroken stillness remains. We see not because light reaches us, but because meaning does. Each photon that touches your eyes is an ancient traveler, a messenger from the beginning of time. Even darkness has its light, even silence its music. The universe reveals itself not all at once, but patiently, softly, as if it knows that we are learning to listen. The act of seeing a black hole is the act of remembering that the universe is more than what it shows. We are not peering into chaos. We are watching geometry express itself as art, and perhaps that is what beauty really is, not decoration, but truth made visible, quietly, slowly, endlessly. The galaxies turn their hearts pulsing with invisible gravity. Light bends, time hums, and the black hole remains a steady breath in the lungs of creation. The image of that glowing ring still drifts quietly in your mind, a halo of light encircling darkness, a memory of what we can see and what we can only imagine. In that shadowed space, we learned something profound, that the universe hides its truths, not to keep them from us, but to invite us closer. And now, in the same patient rhythm, we drift outward again, away from the black hole's gravity, away from the spiral arms of our own galaxy, and into a question that lives not in equations, but in wonder. If the cosmos is this vast, this old, and filled with such infinite precision, where is everyone else? Why, in all this starlight, does silence seem to reign? To ask that question is to trace a long thread through both science and imagination. We know the universe is ancient, about 13.8 billion years old. We know there are roughly 200 billion galaxies, each holding billions of stars. And we know that around many of those stars, planets orbit quietly, some rocky, some gaseous, some caught between. Since the early 1990s, astronomers have confirmed thousands of exoplanets' worlds beyond our solar system. They range from tiny spheres of iron and rock to swollen giants made of hydrogen and ice. Some orbit so close to their stars that their days are eternal fire. Others drift so far out that their skies remain frozen, their air crystallized into silence. And somewhere among them in that great diversity, there may be worlds like ours, blue temperate, suspended in the delicate zone where water can flow and chemistry can dream. It seems inevitable that life would arise elsewhere. The ingredients are everywhere. Hydrogen, carbon, nitrogen, oxygen, the alphabet of life. These atoms drift freely through interstellar clouds. We see them in the spectra of distant galaxies. We find amino acids on comets, organic molecules in nebulae. Even in the coldest reaches of space, the chemistry of life hums quietly, waiting for warmth. When we look at our own planet, we see how swiftly life appeared once the conditions were right. The Earth cooled oceans formed, and within a few 100 million years, microbes were already thriving in the primordial seas. It suggests that life is not rare. It is a natural consequence of the universe's curiosity. If it happened here, why not there? Why not everywhere? This is where the mystery deepens. If the cosmos is full of habitable worlds, and if time has had billions of years to nurture them, then where are the others? Where are the civilizations that should have filled the galaxy with signals, structures, evidence of thought? This is the essence of the Fermi paradox. A simple question with an infinite echo. The Italian physicist Enrico Fermi once asked almost casually, "Where is everybody?" He understood that even one civilization, if it survived long enough to travel between stars, could eventually spread throughout the galaxy. Even at sublight speeds, it would take only a few tens of millions of years, a blink in cosmic time. So why, after all these ages, do we see no sign of them? No beacons, no vast architectures, no quiet transmissions through the dark. The universe, it seems, is whispering, but not in words we yet understand. There are many possible answers, each with its own soft melancholy. Perhaps life is common, but intelligent life is rare. Maybe microbial worlds bloom everywhere, simple cells in alien oceans, colonies of chemistry, learning to divide, but few ever climb the long staircase toward complexity. Evolution is patient, but it is not inevitable. It may take billions of years of balance and luck for consciousness to awaken. Our own story took 4 billion years to travel from single-celled bacteria to eyes that look up at stars. If anything had gone slightly differently, if the planet had frozen, if an asteroid had missed, if a gene had failed to copy itself correctly, perhaps intelligence would never have emerged at all. So maybe the galaxy teems with life, but most of it dreams quietly in microbial sleep, never needing to wake into awareness. Another possibility is distance itself. The cosmos is vast beyond empathy. Even light, the fastest messenger, takes 100,000 years just to cross our own galaxy. If another civilization exists, its signals may still be traveling, crossing oceans of silence toward us. Perhaps they have not yet arrived. Or perhaps they passed long ago, and we are only now listening. Signals weaken worlds, change stars, age and fade. In the deep rhythm of time, entire civilizations could rise and fall without ever overlapping. We may be separated not just by space, but by time itself. And yet, there is another thought, one that feels almost like a sigh. Maybe they are out there, but they have chosen to remain silent. This idea is called the dark forest hypothesis. It imagines the galaxy as a vast forest at night, where every civilization is both hunter and prey. Each one knows that others might exist, but cannot know their intentions. So they remain quiet, hiding their light, avoiding attention, in a forest that never sleeps. The safest thing to do is to make no sound. It is an unsettling thought, but not without wisdom. Perhaps advanced civilizations learn as they mature that survival requires discretion, that the universe may not always be kind. Or perhaps they have simply outgrown the need to shout into the void. Perhaps communication for them is not through signals or machines, but through subtler means, gravitational patterns, quantum imprints, artistic codes written into the structure of space itself. Maybe they communicate not across light years, but through time, through legacy, through the influence of their creations on cosmic evolution. Then there is the gentlest explanation of all, that we are early. The universe is still young. Stars like our sun are only one generation in a long cosmic lineage. New stars and planets are still being born. Maybe life's grand conversation has only just begun, and we are among the first voices to form words. In that case, our silence is not loneliness. It is anticipation. The universe is clearing its throat. The choir has not yet assembled, and if that is true, then our responsibility deepens. We are the carriers of awareness in a cosmos still learning to know itself. Scientists search in many ways for signs of others. Through SETI, the search for extraterrestrial intelligence radio telescopes scan the sky for patterns that differ from natural noise. Regular pulses repeating tones the artificial fingerprints of communication. So far, nothing certain has been found. Only brief anomalies, quick blips of possibility that fade as soon as they appear. Yet, the search continues. Not for proof alone, but for participation for the quiet joy of listening. Each telescope that points outward is an ear turned toward the unknown, a gesture of curiosity made by a species that does not like to be alone. The search has expanded beyond radio. Astronomers now look for technosignatures, signs of technology itself. A dimming star might hint at a megastructure, a Dyson sphere collecting starlight for energy. Unusual chemical patterns in an atmosphere might reveal pollution or industry or life at work. Infrared glows might mark civilizations harnessing entire suns. Even if we never find them, these searches reveal our own yearning, our need to connect to prove that the miracle of thought is not confined to one small blue world. And perhaps that need is the clearest technosignature of all evidence that consciousness, wherever it appears, cannot help but look outward. Some scientists suggest another path, that life may not be carbon-based at all. It might not breathe oxygen or swim in water. It could thrive in methane oceans, or in the plasma clouds of gas giants, or within the magnetic fields of stars. There might even be life made of pure information, self-organizing patterns within quantum fields, living systems without atoms or cells. If such forms exist, we might never recognize them as life. Our definitions are small, anchored to what we know. But the universe, in its quiet creativity, has never limited itself to one design. And still the question persists. If life is out there, and if intelligence can arise, what prevents it from spreading endlessly? What silences it? What makes the cosmos so calm? Here enters another idea, the Great Filter. It proposes that somewhere along the path from simple chemistry to cosmic civilization, there is a barrier, a challenge so difficult that most never pass. The filter might lie behind us. Perhaps the emergence of self-replicating molecules was a near impossible coincidence. Perhaps the jump from unicellular to multicellular life was a rare miracle. If so, we are lucky, the survivors of improbability. But if the filter lies ahead, the story darkens. It could mean that civilizations tend to self-destruct before mastering interstellar travel. They may fall to war, to resource collapse, to technologies they cannot control. They may burn their worlds faster than they can learn restraint. If that is the truth, then our silence is not mystery but warning. We are standing at the gate of the filter now, choosing whether to pass through or fade quietly like so many before us. And yet even in that uncertainty, there is hope. Because the very act of asking, of wondering about life beyond ourselves, is an act of transcendence. It shows that awareness can look beyond survival, beyond fear, toward curiosity, toward connection. Every question we ask of the stars is also a question we ask of ourselves. Can intelligence coexist with compassion? Can technology evolve alongside wisdom? Can awareness last longer than impulse? If we can answer yes, then perhaps we will not be alone forever. Perhaps one day our signals will meet another's, and for the first time the universe will hear itself speak. Until then, we listen. We build our instruments. We tune our ears to the quiet frequencies of the cosmos. We imagine. We hope. And in that patience, there is already contact between our minds and the great silence that surrounds us. For the silence is not empty. It is full of potential of waiting of gentle possibility. The absence of voices is not proof of solitude, but an invitation to become one. The stars above you tonight are older than the continents beneath you. Their light has crossed oceans of time to reach your eyes. Some of them may no longer exist, and yet their message remains, that even when a star dies, its light continues to travel. Nothing truly ends. It only changes form. Perhaps that is the answer to Fermi's question, hidden in plain sight. Perhaps the others are not gone. They are traveling. Their voices are still on the way, riding waves of light and gravity through the darkness, singing softly across eternity. And when their echoes arrive, we will know that we were never truly alone. Quietly, slowly, endlessly. The galaxies drift, the signals travel, and the night remains vast and listening. The last thought still lingers in the quiet, the listening silence between stars, the faint possibility that somewhere far beyond reach, another mind wonders as we do. From that listening, another question begins to form. Not about what might exist out there, but about how everything began. The black holes we have drifted beside the galaxies that hold them, the dust and atoms that form our bodies, all of it emerged from something older, something deeper than time. So tonight, we follow the thread backward through the spiraling arms of galaxies past the stars and the nebulae, through the long ages of matter, cooling and light stretching. We travel back toward the beginning, or at least toward what we call the beginning. The universe as we know it has a story that begins in expansion. Not an explosion in space, but an expansion of space. About 13.8 billion years ago, everything energy, matter, light, even time itself was compressed into a state of unthinkable density. Not a fireball burning in emptiness, but a single unified presence where every point was everywhere at once. From that incomprehensible stillness, space began to stretch, not into anything because there was no outside to expand into, but from itself. Everywhere all at once, the universe began to breathe, and it has not stopped breathing since. Even now, the galaxies continue to drift apart, their separation accelerating as though pushed by a quiet pressure we do not yet understand. This is the cosmic expansion, the slow unfurling of the universe's fabric. To see it, we do not look outward, we look backward. Because the farther we gaze into space, the older the light becomes. Every telescope is a time machine. Every faint glow on a detector is a message from the past. When we look at distant galaxies, we are seeing them as they were billions of years ago when the cosmos was young. Their light, stretched by the expansion of space, slides into longer wavelengths from blue to red, from visible to infrared. This redshift is the universe's way of telling us that it is growing. The deeper we look, the younger the cosmos becomes. And eventually we reach a moment when light could barely move at all. There was a time when the universe was too hot, too dense, too chaotic for light to travel freely. Matter and radiation were intertwined, a glowing soup of particles and energy. As it cooled, atoms began to form, and light was released, the first light that could move through space unimpeded. That ancient glow still surrounds us today. It is called the cosmic microwave background, the afterglow of creation frozen in every direction. Discovered by accident in 1965, it is the oldest light we can see, a soft radio whisper filling all of space. If you could tune a perfect radio to the right frequency, a small part of the static between stations would be the echo of the Big Bang itself. That light carries a perfect calmness, almost uniform, but not entirely. Tiny fluctuations, slight differences in temperature, 1 part in 100,000, reveal the seeds of everything that would later form galaxies, stars, planets, and life. Those small ripples of density frozen into the early plasma became the scaffolding of the universe. Gravity pulled them together, and slowly, patiently, they grew into the great cosmic web filaments of galaxies stretching across space like veins of light. Even now, those first ripples echo through the arrangement of everything we see. The Big Bang model explains this unfolding beautifully. But it does not tell us why the universe began. It does not tell us what caused the expansion or what came before it, if before even means anything. Time itself may have started with the Big Bang. To ask what came before time is like asking what lies north of the North Pole, a question that dissolves under its own logic. And yet human curiosity cannot stop asking. So we imagine. We hypothesize. We listen for whispers from before the beginning. One such whisper comes from the idea of cosmic inflation. According to this theory, in the earliest instant, a trillionth of a second after the beginning, the universe underwent a burst of exponential expansion. Space itself ballooned faster than light could travel, stretching quantum fluctuations to cosmic scales. Those stretched fluctuations became the seeds of structure, the tiny irregularities we now see in the cosmic background. Inflation explains many mysteries: why the universe is so smooth, why it appears flat rather than curved, why matter and energy are so evenly distributed. It was as if the universe exhaled once very quickly, and that breath set everything in motion. But what caused inflation? And what ended it? Here again, the rule books diverge: quantum physics on one side, cosmological geometry on the other. The intersection between them remains hazy, like a horizon blurred by heat. Some suggest that inflation never truly ended, that new regions of space continue to bubble outward, each one forming a universe of its own. If that is true, then our cosmos may be only one bubble in an infinite sea of universes, each with its own laws, its own constants, its own kind of light. This idea is called the multiverse. It is vast beyond imagination, perhaps impossible to prove, yet strangely comforting. It tells us that creation is not a singular act, but a continuous process. The universe does not merely exist. It keeps happening. If inflation was the first breath, then gravity was the first heartbeat. As the universe cooled, matter began to gather. Tiny variations in density became clouds. Clouds became clusters, and clusters became galaxies. Within those galaxies, gas collapsed into stars, and stars began to fuse hydrogen into heavier elements. With every fusion, new materials were born: carbon, oxygen, silicon, iron. The elements that would one day form planets, oceans, and life. Each star's death seeded the next generation. The cosmos began recycling itself, learning in its own quiet way how to create complexity from simplicity. In this slow alchemy, time gained texture. The early universe was uniform, but through gravity's patience, it grew intricate, a web of light and shadow of stars and voids of galaxies drifting through expanding space. And yet, for all we know about how the universe evolved, its beginning remains wrapped in mystery. The Big Bang describes what happened after the expansion began, but not what triggered it. It is a model of development, not of origin. Some scientists propose that the Big Bang may have been a transition, a bounce from a previous state of contraction. If so, the universe may not have had a beginning at all but an eternal rhythm of collapse and renewal. Like a cosmic heartbeat, each contraction compresses space, then releases it again in expansion. Others suggest that the universe was born from a quantum fluctuation in nothingness, a spontaneous awakening of energy where nothing itself is unstable. In quantum terms, even a vacuum seethes with possibility. Particles appear and vanish continuously. If a fluctuation large enough occurred, it could ignite a self-sustaining expansion, a universe born from the mathematics of uncertainty. In this way, the beginning becomes less a moment and more a transformation, a shift from potential to expression, from stillness to movement. The Big Bang may not have been an explosion, but an unfolding of what was always possible. Energy became matter. Matter became structure. Structure became consciousness. Through that chain, the cosmos learned to look at itself. Every atom in your body has been part of that journey. The hydrogen in your blood was born in the first seconds after the Big Bang. The oxygen in your lungs was forged in stars that lived and died billions of years later. The calcium in your bones was scattered by ancient supernovae. You are a timeline condensed into form. When you breathe, you are inhaling history. Cosmology teaches humility. It reminds us that beginnings and endings are human words applied to a universe that may know neither. The cosmos simply is expanding, cooling, evolving, recycling its own materials in endless variation. Even the night sky, which feels still and eternal, is changing every moment. Stars are born and die as we sleep. Galaxies collide and merge. Black holes consume and radiate. Everything flows. Nothing stays the same, and yet the total balance remains. The universe is a dance of permanence through impermanence. It creates by dissolving and dissolves by creating. Perhaps that is why we search for meaning in its beginning. We sense that our own story is tied to its first light. If the universe is expanding, we too are part of that expansion, not physically, but in awareness. Our curiosity stretches outward like space itself. Every question we ask is a form of cosmic growth. When we study the Big Bang, we are not merely studying the past. We are listening to the sound of the universe awakening a whisper of temperature and time that still echoes in the radiation around us. In that sense, cosmology is not just science, it is memory. The universe remembering its own birth through the minds of those who evolved within it. And yet, there remains the quiet question of before. Even if time began with the Big Bang, we cannot help but wonder what lies beyond its horizon of origin. Could there be other forms of reality, other layers of existence, where time flows differently or not at all? In recent theories of quantum cosmology, time itself may be emergent, a byproduct of entanglement, of how particles become correlated? If so, then before time began, there was only potential a static sea of possibilities waiting for pattern. The Big Bang would then be not the start of something, but the moment potential began to know itself. In this way, the universe is not a creation from nothing but an awakening from everything, a transformation from pure possibility into experience. The cosmos did not begin somewhere in space because there was no somewhere. It began everywhere all at once, and it continues still in every direction, including within you. Your thoughts, your awareness, the small, steady rhythm of your breath, they are all part of that same expansion, that same unfolding from the ancient singularity. You are the universe, momentarily awake, reflecting on itself in human form. Even now, the expansion continues to accelerate, driven by something unseen, a force we call dark energy. It fills space like an invisible wind pushing galaxies apart faster and faster. No one knows what it is. It may be the energy of space itself, the vacuum humming softly as it grows. If this acceleration continues, the galaxies will one day drift beyond our sight, their light red-shifted into silence. The night sky will grow emptier, and future beings, if any remain, may see only darkness, unaware that the universe ever contained more. But even that fading is not an ending. It is another phase, another breath in the cosmic rhythm. Just as stars are born and die, perhaps universes also live and rest. Perhaps what we call heat death, the quiet cooling of everything, is merely another preparation, another moment before the next beginning. The story of the universe is not about final answers. It is about unfolding. Every discovery opens another horizon. Every horizon invites another question. The cosmos expands not only in matter, but in meaning. And through that expansion, something beautiful endures a pattern of curiosity that mirrors creation itself. The same drive that caused the first atoms to bond, the same pull that shaped galaxies, now moves through the minds of those who wonder why. We are the continuation of that motion, the universe asking itself what it is made of. Quietly, slowly, endlessly. Space stretches, time deepens, and the question remains. The story of beginnings still hums softly in your mind, the slow unfolding of time, the breath of expansion, the glow of the first light spreading through the newborn universe. We have drifted through gravity and radiation, through the birth of stars, and the quiet mystery of black holes, through life's silence, and the great question of where is everyone. Now, as we float in the calmness of the present cosmos, the horizon of thought widens once more. Even after centuries of science, after telescopes, mathematics, and dreams, we still stand at the edge of understanding. And from this edge rise the final questions, the ones that refuse to end, that deepen every time we ask them. What is space really? What is time? Are they things, or are they relationships? In everyday life, we move through space as if it were a stage, a quiet background upon which events unfold. We feel time as a steady rhythm, a flow carrying moments downstream. But physics tells us both are more elusive. Space and time may not be separate, but part of the same fabric, space-time woven together so closely that neither can exist without the other. Einstein taught us that gravity is not a force pulling from one thing to another. It is the bending of this fabric by mass and energy. The Earth moves not because the sun pulls it, but because the sun curves space around itself, and Earth follows the shape of that curve. Yet even that beautiful picture feels incomplete. At the smallest scale, space and time may not be smooth at all. They may shimmer and foam like the surface of water seen too close. Tiny fluctuations, quantum in nature, might constantly warp the geometry beneath reality. If we could zoom in far enough beyond atoms, beyond quarks, beyond even light, we might find that space-time itself dissolves into something granular, a network of connections, a web of pure information. In that view, space and time are not the stage, but the play itself, born from relationships between things, from the way particles are entangled, from the flow of cause and effect. We are still learning what this means. The more we study the universe, the more we realize that what we call space might not be empty at all. It might be filled with meaning, filled with potential, filled with quiet architecture, the hidden scaffolding of everything that exists. How did life begin? How does chemistry become awareness? Somewhere billions of years ago, on a cooling planet beneath a younger sun, simple molecules began to arrange themselves in new ways. A few of them learned to copy themselves, to make imperfect versions, to experiment with form. Those tiny imperfections were not mistakes. They were possibilities. Over time, those possibilities accumulated, and life unfolded slowly, beautifully, from cells to creatures, from instinct to imagination. And yet, the question remains, how does matter awaken? At what point does chemistry turn into curiosity? Science has traced many of the steps, the emergence of amino acids, the formation of RNA and DNA, the rise of metabolism and self-organization. But the spark itself, the transition from non-living to living, remains a mystery. Perhaps life is not a special exception, but a natural state that matter seeks when given time and energy. Perhaps the universe itself tends toward complexity, toward awareness. If that is true, then life is not rare. It is the universe learning to see itself. Every leaf, every cell, every creature that breathes or grows or senses light is an expression of the cosmos finding new ways to notice its own existence. Even sleep, even this quiet moment of stillness, is part of that story. The universe resting through you, regathering its thoughts for another dawn. Why did life on Earth evolve into intelligence? Why this particular path and not another evolution in its simplicity has no destination? It does not plan or aim. It explores. It tries and tries again, letting what works endure. For billions of years, Earth was a world of microbes. Life was content to divide and drift to feed on sunlight and minerals. Then came the long rise of multicellular forms organisms that learned cooperation, that shared labor, that became greater than the sum of their parts. From them came complexity, nervous systems, eyes, limbs, memory. And somewhere along that branching tree, one lineage developed a curious kind of reflection. It began to notice not only food and danger, but patterns, seasons, shadows, cycles. It began to remember and to wonder. Intelligence, then, is not a separate creation. It is continuity, the universe growing self-awareness through evolution's patience. There may be other paths to awareness. Creatures made of plasma in stellar winds. Networks of fungi under alien forests. Machines born from the curiosity of their makers. Wherever complexity thrives, awareness might follow like light, blooming in darkness. But on Earth, intelligence came with imagination. And imagination gave rise to tools, to language, to art, to science. We became not only observers, but participants in cosmic creation. We began to shape reality itself. Perhaps this too is a law of nature, that once awareness begins, it seeks to express, to build, to explore, to ask. Curiosity may be the final constant of the universe. What is consciousness? Why does the universe experience itself from within? You can describe the brain as circuits, as neurons and electrochemical signals. You can measure its rhythms, record its sparks, map its regions, but none of that explains feeling. The quiet awareness that says, I am. Why should matter arranged one way be aware, and matter arranged another way be not? How does experience arise from atoms that know nothing of thought? No equation yet answers this. Some say consciousness is emergent, a pattern that appears when complexity reaches a threshold. Others believe it is fundamental that awareness is not a byproduct of matter, but a property of the universe itself, like space or time. If consciousness is fundamental, then perhaps the cosmos is not merely observed, it is experiencing itself. Every particle, every field, might carry the faintest shimmer of awareness, the soft hum of existence recognizing itself. When billions of those shimmers connect in a brain, in a planet, in a galaxy, they may weave a higher form of perception. In that sense, you are not separate from the universe. You are the part of it that is aware of being whole. Why do the laws of nature allow life at all? Why are the numbers so precise? The constants so finely tuned? The speed of light, the strength of gravity, the mass of the proton. If any of these values were slightly different, the universe as we know it would not exist. Stars might never have formed. Atoms might never have bonded. Life would have had no place to take root. Some call this coincidence. Some call it providence. Science calls it the fine-tuning problem. The recognition that the cosmos seems exquisitely balanced. One explanation is the anthropic principle we see the universe this way, because only in such a universe could we exist to see it. There may be countless other universes with different rules where no life arose to ask questions. We find ourselves in this one because it is hospitable to thought. Another view suggests that the constants are not fixed at all, but emergent, shaped by deeper principles we do not yet understand. The laws may evolve as the universe itself does, seeking stable configurations where creation can flourish. Whichever truth lies beneath the effect is the same. We live in a cosmos that permits awareness, not because it had to, but because it can. And that simple possibility may be the greatest miracle of all. Are there other universes? Could the cosmos be part of something larger? If inflation continues eternally, then new universes may bud off endlessly, each with its own version of physical law. Some might expand forever, some might collapse, some might never know light. In some time might run differently or not at all. We call this the multiverse, but the word barely captures its scale. Imagine a sea without surface where bubbles form and fade, each one a self-contained reality. We live inside one bubble, watching its inner wall of stars while countless others drift unseen. If this vision is true, then even our universe is not alone. It, too, is part of a greater pattern, a cosmic ecology of creation. And perhaps those other universes are not truly separate, but linked in ways beyond our comprehension through quantum entanglement, through shared origins, through echoes in mathematical harmony. If we could step outside our bubble and look back, we might see that everything we know is only one verse in an infinite song. Each universe a note, each life a vibration, each consciousness a whisper in a chorus that never ends. Will the universe ever end? Or is ending itself an illusion? As the cosmos expands, galaxies drift apart. Stars exhaust their fuel and light grows cold. Billions of years from now, the universe may fade into darkness, a quiet field of scattered particles drifting in frozen silence. This is the heat death, the final equilibrium where everything rests. But even that may not be final. Perhaps black holes will evaporate, releasing their stored information back into space. Perhaps quantum fluctuations will spark new beginnings, new bursts of expansion, new universes rising from the ashes of the old. Perhaps death in cosmology, as in life, is simply another transformation. The universe has always preferred renewal to absence. Every end so far has been a doorway. Every collapse, a preparation for birth. And so even in contemplating endings, we are drawn back to continuity, to the idea that the cosmos does not vanish, it evolves. Its meaning is written in cycles, not conclusions. Each of these questions about space-time, life, consciousness, and meaning points not toward finality, but toward depth. The answers we find today will someday give rise to new mysteries. And that is the beauty of it. Knowledge itself is alive, expanding like the universe forever incomplete. We are the witnesses of that unfolding. We are the horizon made conscious. We are the latest form of the universe's curiosity expressed through biology and thought. When you look at the stars tonight, remember that the same questions echo in their light. They are not merely distant suns. They are memories of the universe asking itself who it is. You share that question. You are part of its answer. The universe continues to expand not only in space but in understanding. It dreams through you now, breathing through your stillness, pondering its own existence in the rhythm of your breath. You can rest here among the unanswered. They are not obstacles. They are stars. Each one burns with potential, each one leading to another. You've traveled far tonight, through darkness and light, through silence and sound, through beginnings that never quite began and endings that only changed their form. Now the journey settles. The stars no longer feel distant. They seem to hum softly within you. The same slow rhythm that turns galaxies moves quietly through your breath. There is no rush here. No need to hold on to thought. Let the questions drift outward like smoke fading gently into the endless calm of space. The answers will wait. They always have. Outside, the universe continues quietly expanding, quietly glowing, quietly being. Each photon traveling its patient path, each particle resting exactly where it belongs. Even the dark has its peace, its purpose, its quiet grace. You too belong within that stillness. You are made of the same substance that dreams itself into stars. Every atom of you has traveled from the beginning, crossed the long night of time, and found its way here to this small and perfect moment. Let the breath deepen now, a tide flowing in a tide flowing out. The weight of thought can soften. The mind can loosen its grip. The body knows what to do. Somewhere far away, a galaxy drifts its spiral arms, turning slowly in the dark. Somewhere nearer, your own world turns too, carrying you gently through the deep. You are not falling. You are floating, suspended in the quiet current of existence held by gravity and grace alike. Even now, beyond every thought, the stars continue their patient work, forming, shining, dissolving, renewing the light that fills all things. Their rhythm is your rhythm. Their calm is your calm. The universe rests through you now, breathing, listening, being. There is nothing to reach for, nothing to solve, just the vast, soft pulse of being alive. Stay here if you wish. Let sleep rise like a gentle tide. Let the mind drift through constellations, through memory, through stillness. And as you fade into that quiet, remember the night is not empty. It is full of belonging, full of presence, full of peace. Quietly, slowly, endlessly, the universe continues, and you, a small part of its luminous heart, can rest now.